Hello and welcome to yet another in our series of webinars from A3 Management Consulting. Thank you very much for joining. Very pleased to have you joining us, whether it be morning or afternoon where you are, or indeed nighttime. Today we're going to be talking about a very important subject, and I think really following on from the webinar on the 4th of June, where if you want to catch up on past webinars, they're all available on the website. Just drop one of us a line or Google for A3 Energy webinars and you'll find the page easily. But on the 4th of June, we were talking about climate-related financial disclosure and how that was becoming more and more important. And as we head towards 2022, we're expecting vast majorities of organizations, of corporations to be impacted and having to do some reporting if they're not already. So today we're going to talk a little bit about actually following on from that, how we go about quantifying the impact of climate change. And I hope you will enjoy the session today. So if you could kick on through the disclaimer slide, please, and onto the presenters. So there's three of us here today. I'll just briefly introduce myself and then ask my colleagues to introduce themselves. So my name is Matt Brown. I'm Vice President at A3 Management Consulting, looking after the energy area and a lifelong interest in the energy environment interface especially. So I'll hand over to either you, Philipp, or you, Klaus. Please say hello.
Hello, good afternoon. My name is Claus. I'm a consultant with A3 Management Consulting in Vienna, and I've been there for around a year now. And before that, I was in academia completing my PhD in economics.
Yes, hello everyone. My name is Philipp Ortmann. I'm working with A3 since 4 years now. I'm an economist by training, and I'm mainly focusing on all kinds of power market modeling topics, specifically evaluation of renewables, and very recently also climate-related modeling.
Excellent, thank you both. If you could just kick on to the next slide. Then just some housekeeping. First of all, 45 minutes today. We are taking questions all the way through the webinar. We also had questions on registration. We will come to Q&A at the end of the session, towards the end of the 45 minutes. And it's well worth asking questions. We will endeavour to get back to as many people as possible. If we don't answer the question in the webinar, we'll follow up with an email. Please, there are some contact details at the end, so please do follow up there. And then also the webinar itself is going to be recorded, and the slides will be made available, so you'll be able to pick those up as well. So on to the subject at hand, why climate change is important and how we model its impact on the power sector. I think, you know, if we move on to the following slide, it's fairly obvious. I hope we are all aligned that climate change is happening, and actually is the risk of catastrophic climate change is becoming ever greater as we move through time. And you can see here the annual mean temperature. I'm sure a lot of you have seen these sort of charts before, showing how we are moving through into some of the hottest years on record. And I note that we had the hottest temperature recorded just the other week. The other thing you may know, if you know about A3, is that we do a lot of our power market simulation and modeling with historical weather years, and we run a large number of historical weather years in order to understand the volatility and the variability that weather can bring into the future, especially in terms of, you know, the capture prices, the money earned by different technologies in power markets, what revenues they're going to be picking up, what their operational patterns are going to be like. And of course, as more and more renewables come into the system, then we become ever more weather dependent in our electricity system. And it's always been so, of course, in hydro dominated power markets, especially you think of, say Norway, where the snow melt is particularly important, reservoir levels particularly important, or other markets like Brazil, where large hydro resources exist. Then river flow there is vital. So the weather has had an impact and is an ever-growing impact into the future. And the question, of course, we've been asked several times by clients, and we ask ourselves is, what about the future? What about power market modeling with climate change? You're modeling historical weather years, you're modeling quite a range of historical weather years, but what could you say about the future if you were to take into account some of the climate change models? And that's what we're going to really dig into today. So if you move to the next slide, thank you. So what you can see here is concentration pathways, the different pathways from IPCC, and as you may know, climate scientists are building models of the climate. They're getting into fairly high resolution climate simulations for the past and for the future. And what's important is bringing together a lot of different models that are done in different ways and checking how they all move into the future, and you get quite a high degree of agreement on the pathway into the future for climate models. Now we're not building our own climate models, so in this regard what we do is to take the publicly available data that's now coming out of these simulations to conduct our analysis. And in particular, in this case, we've looked at the RCP 4.5 case from the IPCC and use that as a starting point for doing some analysis looking forward to see what the weather impact could be into the future if we were to take climate change into account as best as one can. And of course, up until now, there's a great uncertainty around the climate modeling. It's a question mark of to engage in doing a high degree of sophisticated analysis. To what certainty can you put on the future climate models? But those models are becoming more and more evolved, I would say, and greater agreement going on. So we think now is the time where we can start taking some of this more granular data that's coming out and at least do some what-if analyses. So if we pop onto the next slide. From the bottom up, really, here we have the emissions pathways and climate change, as I say. So regional climate models, we've got the weather patterns, we've got temperature and precipitation. We take the weather impact on the power sector, and you can look at the impact on demand on hydro inflow, and that's what we've focused on so far, really, is demand and hydro inflow. And I'll come on to some of the other things that we could be doing. And then we have this BID3 simulation model. We're taking our central case, we're looking at 2050, and we're taking the different versions of the RCP 4.5, which have slightly different aspects to them in terms of, say, cloud cover, precipitation, and so on. And then we're comparing here our modeling for 2050 under historical climate year versus what a mid-century climate year might look like. And whilst we have a really good range, I would say, within the historical weather patterns, covering a wide range of outcomes, of course, into the future, for instance, the weather volatility might be might not be captured by using historical weather patterns. What's really important about all of this is that we put a consistent set of inputs into the model, and that everything is lined up. So the demand, the the radiation, the precipitation, all of those things in the model are consistent, a consistent set of data. And we're doing that, of course, because we see a need in our client base for understanding what the impact could be. And I could imagine that as a portfolio owner of a large number of renewables, understanding that you might be facing because of a middle path of climate change, a 10% change in your revenues in one part of the world in a positive way and negative in another part of the world or another geography, say in Europe, then that would be quite interesting to assess in order to change your portfolio and understand the risk of your investments. So that's what we're getting into here, and which we're going to explain in more detail. If you move on to the next slide. And as I said, what we've covered here really is the first two, the electricity demand, the hydrology. Climate change is affecting these other things underneath: solar, wind, thermal availability. We are looking to incorporate those in future. For the results we're going to show here and the analysis we've done so far, we've taken these two top elements. The hydrology is really interesting, and it's a very it's a very complicated aspect of the modelling to get that hydrology right for climate change impacts. So that's why we've sort of bitten off those first two. And also because as the temperature changes, of course, we're getting changes in heating and cooling requirements, which are fairly significant. And we've seen some of these things happen in the past. So we've seen hot summers where, for instance, French nukes were turned right down because they were breaching temperature levels in the rivers where they were drawing cooling water. We've seen those sorts of things occurring. We've seen hydro, questions in northern Italy about should you be irrigating, should you be generating electricity, and these things have become, I think, more and more concerning over time. So that's by way of an introduction to what we're going to talk about. I think I'm going to hand over to Philipp now, if I'm not mistaken, with a short poll to ask you some questions.
Yes, exactly. Thank you, Matt. At this point, we would like to do a quick, or actually two quick polls to see where people stand at the moment and what they think, in particular with regards to the relevance of climate change in the power sector. So I think everyone can see the poll now. Okay, very good. Thank you all for your answer. I think the result is relatively clear. It seems that most people have already, I wouldn't say worried, but at least thought about climate change, and they think that there is some risk incurred for the power sector at a certain point. A quick second one would be, what do you think will be the risk that comes with the climate change with regards to your assets and investments? So do you think you're very high exposed, or is the exposure rather low? Cool, very good. Thank you all for your answers. I think the result is also quite striking. Most people think that they are highly exposed to climate change and carry a certain risk. we'll try to figure out what this risk is in the power sector and maybe provide some answers and shed some light on this thing. Thank you so far. We're going to start at this point with a quick overview on what our initial model results for 2050 look like. As Matt already outlined, we have gone through these 3 steps you have seen. So starting from emission pathways towards bit 3 power market modeling. And what we're going to show you now is the initial results of this modeling. Bear in mind that we are talking about the year 2050 in this case. So all the results are based on a central scenario for the year 2050. Basically, what we can observe is that the baseload prices nearly in the entire of Europe are going to weaken, apart from southern countries, so Portugal, Spain, Italy, and Greece, where prices and therefore revenues for baseload generators are going to increase. That is mainly a result from a shift of demands away from winter because temperatures rise into summer, where demand for cooling devices is expected to increase, and this will have a certain effect on prices. Secondly, hydro patterns are going to change. So hydrology is mostly positively affected, at least in Central and Northern Europe, but it's getting drier in the southern countries, which also leads to a certain price increase. Speaking of which, with regards to hydro generators, the picture is turned around a little bit. So hydro generators carry a negative risk in southern countries. So the price increase that we see in the baseload price is offset by a lower volume because hydro generation is going to decrease in southern countries, and on the other hand is going to increase in Central and Northern Europe. So we're talking about a positive volume effect in Central and Northern Europe. Coming to wind generators, investigating the price effects here only, so not talking about the volume effects. It mainly mimics the picture of the baseload prices. So wind generators in Central and North suffer a little bit from weakening baseload prices and are benefiting a little bit from increased prices in the South. The picture for solar generators is also similar to the baseload price structure. Prices are expected to increase in southern countries. So solar generators could potentially benefit from increased demand from cooling, which usually happens during summer and on hot days. In the rest of Europe, the solar generators suffer from a general reduced price level. It's also worth looking at the monthly price signals and the seasonal shape of the prices. So in general, what we observe is that prices are going to decrease during wintertime and increase during summertime. That is particularly striking for Southern Europe. Again, reduced hydro inflow is the reason for it, as well as more cooling demand in summer months. The shape is more or less the same in Central Europe, but the extent differs a little bit. So the curve is a little bit shifted downwards. So the negative effect of the winter months mainly exceeds the positive effect of the summer months from cooling. And last but not least, in the Nordics, the effect is quite striking. It is negative in all months. So there is hardly any positive effect during summer months. The prices decrease in virtually all months of the year. That's it so far with our main model results. At this point, I would like to hand over to my colleague Claus, who will guide us a little bit through our approach on methodology on demand.
Thank you, Philipp. So what I want to try now is to give you a brief run through of our European-wide demand model. So if you look at the next slide, and give you a bit of an insight in what we actually do here. So Matt talked before about the RCP, so the concentration pass out of the emission scenario. So we have this 4.5 scenario, and this translates into a certain temperature level throughout Europe. And we take this temperature levels on a very high resolution set and try to put that into a district level data set combined of the Eurostat NUTS 3 regions. So what is helpful within the NUTS 3 region is that we also have population values for these NUTS 3 regions, meaning that, of course, you know already that the more populated in certain areas, the higher the demand. And so we can actually provide a population-weighted temperature index for each European country within our demand model. If you look on the left-hand side of the slide, you see actually the temperature signal that comes out of the RCP 4.5 scenario here, and it's the change in temperature within the NUTS 3 region in Europe, and the difference in time periods between the time period 1990 to 2004, so the difference in means, and versus the time period 2043 to 2057. And what you see here on this graph is, for example, that in the Alpine regions, the increase in temperature is already quite high in the mid-century, and also in the Pyrenees, for example. On the other hand, in the UK, the increase in temperature is slightly lower, so about 1.5 degrees centigrade. So you see there are differences in the temperature values we get out of these emission paths. But what you also see is that they are more or less uniform, or a little bit more uniform than what you will see when we talk about hydrology later on. So in the next slide, I would like to give you a little bit of rundown on what we do when we model a daily demand as a function of temperature for a given country. So what we start out with is that we have certain historical load points, and these load points are plotted here at gigawatt hours per day, for example, on a temperature they occur with. So we have historic temperature and we have historic load points. And what we try to do is then we fit these load points to a certain historical demand. And with this fit, then we are able to actually try to project what happens in the future when the temperature signal changes afterwards. So when the temperature is actually going up. And for this case, first of all, in order to predict future demand, we need to find out what is the base demand. So with base demand, we mean a demand that is independent of temperature. So meaning that no matter whether temperature goes up or down, this is always the same demand that is used in a given country per day. So, and of course, within this base demand, we also account in our modeling for increase in electrification coming, for example, from electric vehicles or other things. The other thing, and more importantly, when we're talking about climate change signals and climate change signals from temperatures, of course, if we look on the left-hand side of this fit curve, then we see that if we are accounting for electric heating as a falling function of temperature. So what we need to do here is to identify what is actually the capacity of heating in the future, of electric heating in the future, and what is also the load factor of electric heating in the future when we're considering temperature increases. And this, of course, then defines how much heating is actually coming into place in future values. The same is true if you look on the right-hand side of the figure under the fit until the base demand. If we look at electric cooling, it's also a function of temperature and, of course, increasing. So the higher the temperature, the higher the cooling capacities that will be installed and also used. And all of this then combines our basic demand model in order to predict future temperature or future demand actually, and when we have future different temperature signals from the RCP scenarios. So this is the basic rundown of the model, and this is an illustrative case, and I just want to show you on the next slide that, for example, if you look at Italy and the daily profile for 2050, and you have in the x-axis the days here, so from 1 to 365 in the year 2050, then you see that there is a certain heating amount needed in the winter months, and there is a certain cooling amount needed in the summer months. And what's also interesting and a little bit hard to see, I guess, is but the gray areas here is the base demand, and with these camelbacks here, you see actually that the base demand is also differentiated between weekends and weekdays. So there is a different base demand on weekdays and a different demand or base demand on weekends. So this model also accounts for this weekday effect of the base demand. Coming to the last slide of the demand modeling section here, And this is really something that wraps up a little bit the results. So the key message I want you to take away from here is that the total net demand reduces for almost all European countries. So there is a reduction of the heating demand, and this reduction actually outweighs the increase in cooling demand. If we again compare the time periods of the mean or the means of the time periods 1990 to 2004 and versus the means of 2043 to 2057, taking into account the already installed capacities in 2050 for heating and cooling. So what you see on the left-hand side is that for almost all European countries, the average net demand goes down. And for example, particularly in France, because they have a lot of electric heating, which is replaced, of course, by other heating technologies. But in the end, of course, by increasing the temperature with the temperature signal out of the RCP 4.5 scenarios, this heating volume goes down a bit. Again, it's not by much. So you see the scale here, it's not an awful lot if you consider the whole Europe consumes about 3,500 terawatt hours. It's not a much, but at least it gives a mid-century signal where this journey is actually going. On the right-hand side, you have, and it's also interesting to see that there is actually a seasonality pattern as well in the average demand difference. So again, this is the difference between the two time periods. And what you see here is that especially in the winter months, the demand for heating is going drastically down. And again, you see that it outweighs the increase in cooling demand in the summer months from June, July, and August and September. So to wrap up a little bit our demand model, it's population-based or population-weighted index of temperature, which uses then also capacity expectations on heating and cooling demand in order to get a sound and sophisticated overview of our of demand in the mid-century, given that we're using the 4.5 emission scenario and the translated temperature that ensues that. So with that, I would like to hand over again to Philipp to talk a little bit more about the hydro.
Very good. Thank you, Klaus. In a similar way, so with a similar bottom-up methodology, we have also approached hydrology. We started to look at the weather signals first of all. So investigating the average runoff signals of each significant river basin in Europe shows that the runoff signal is rather diverse across Europe. So whereas the temperature signal was rather uniform across Europe, in this case it becomes evident that the runoff of rivers is quite diverse across Europe, where southern countries like Portugal, Spain, and the Southern Balkans in particular suffer from drier weather and less river runoff. How did we come up with these results? A little bit of methodology behind. The basis for these results is the so-called rainfall runoff modeling, which is definitely a separate branch of science that is dedicated to this field. We have this competence within AFRY, so that is an in-house specialty of us. But in this case, we have referred to publicly available data by the Swedish Hydrometeorological Service, which provides this data on the basis of this RCP emission pathways and does the rainfall runoff modeling. In this respect, it is also worth mentioning that the river runoff is a result of the temperature as well as the rainfall. So it's not only the rainfall signal that is evident here, but it's a mix of temperature and rainfall. Talking about evaporation on the one hand in southern countries, and also temperature decides whether rainfall comes down as snow or actually as rain. So these factors are already accounted for to come up with meters cubed per second for each significant river in Europe. In the next step, we have then simulated energy volumes, as we want to run a power market model we need to deal with energy volumes. So we have translated this inflow in meters cubed per second, together with the net and gross head of each power plant and their respective efficiency values, into a hydro inflow in gigawatt hours per day. Let's have a quick look at the first results. We have chosen a bottom-up approach, so we have literally modeled each significant hydropower plant in Europe and translated the inflow into energy volumes. What is evident again is that in southern countries the inflow is expected to decrease, whereas in Central Europe and the Nordic region the inflow is expected to increase due to more precipitation and more rainfall. The size of the points here indicates the size of the respective plants. If you wonder why there are black dots, the black dots indicate pump storage power plants, which actually have no inflow or no significant source of inflow, but we have included them and accounted for in our power market modeling. So they are not exposed to any climate signal, but they are relevant for modeling the power market in this field. Again, also it makes sense in this respect to look at the seasonal patterns. So again, the seasonality is different across different regions. So in the Nordics, or in general, it is evident that the inflow increases in winter months and decreases in summer months, but the extent is different across regions. So in the Nordics, the positive effect of the winter outweighs the negative effect of the summer. And in Southern Europe, the negative effect of the summer months exceeds the additional inflow during winter months. Well, this basically wraps up our main results. I would like to conclude here and start with another quick poll. In this respect, I have just seen that I have not shared the old results with you of the old poll. So what I was referring to is that most people see their exposure to their assets and investments rather high in this case. But in this respect, I would like to conclude with a final question, namely, what do you think of the RCP 4.5 and the results on the mid-century? Is the RCP 4.5 too aggressive, too conservative, or what is your feeling about that? Very good. Thank you so far. I think we are pretty on a good track. It seems that we are on a good track with our choice of 4.5 in this case. Most people think we are right, but of course there is also a certain risk that we are too low in this case and we are actually running into a more worst case scenario in reality. Thank you so far. At this point, I would like to hand back over again to Matt Brown, who will conclude with a couple of key messages and wrap up with a quick conclusion.
Lovely, thank you very much. So we've taken you through our sort of first steps in modelling here of the climate change. I think what we see is that there are impacts, and as we add, I think the solar, the wind, the thermal to this analysis, then we'll see bigger impacts coming through. Even fairly small changes, of course, in the future can have quite a big impact on profitability for some of these assets. And I must admit, I agree with the around about 32% of you who are saying that the RCP 4.5 is most likely too low. And I was relaying to my colleagues earlier in the week that in about 1992, when I was doing a master's in environmental technology, took the energy option, we were talking about not breaching 350 ppm, and of course, you know, during my time working in this field, then we've gone through 400 already. I think, you know, we're probably all of us on this webinar focused on doing our best to make sure that we're mitigating the impact of climate change as much as possible. So if you want to kick on to the conclusions, because it's a fascinating subject area to be working, and I always feel very lucky to be working in this area. Energy, climate change, and the future, where we're headed. So we've had a first stab here. You can see our conclusions. Physical climate change risk within the power sector, looking at the impact on demand and on hydro so far. And within that context of taking our standard scenario and comparing 2050 with a future world where we've taken account of these climate change models that we can access, then these are the results. This is what we see. We see impact different north and south, and different, of course, for most technologies other than hydro, where there's a reverse, where we're seeing reduction for most technologies for Central and Northern Europe, and Southern Europe having a net benefit. The climate impact is reducing net demand for almost all European countries. And of course, remember, when we're looking at 2050, we've electrified a lot of heat demand in our modeling, in our Hestia model, that's the model of the heat sector, within our BID3 framework. So the impacts you saw there on demand already take account of the fact that we would have electrified a lot of heating throughout Europe, especially those countries where there's still a high reliance on, for instance, gas boilers in the home, like in the UK where I live. Seasonal patterns change, but you know, the reduction in heating is more important than the increase in sort of volume term in cooling demand. Although, of course, it's having an impact in some of the hotter countries in increasing peak demand overall. And if you just click once more, I think we have the next steps that we're aiming to follow up. As I say, taking wind, solar PV, thermal availability, looking at different cases as well on the concentration pathways, and of course, doing asset-specific analysis, which is something we do a lot of for many of our clients, looking at the impact of all sorts of future uncertainties. So with that, I think we've finished the main part of the webinar. We'll open it for Q&A, which I think has its own little slide on the next page. So let me have a look here on the questions. So the first one I have here: what impact do climate change effects have on security of electricity supply? Perhaps Klaus, you can take that one.
Sure, thank you, Matt. So within the security of supply concept, I mean, it really boils down to the question whether end users can be provided with the specified level and also continuity and quality of electricity at their point of delivery. So, I mean, what I mean is that end consumers need to get the electricity they demand from the system. So if we now have kind of laid my way around the demand system because I was modeling that within the analysis. So if we're looking at the climate change effects with regards to demand, and also looking what we have discussed now in the webinar, so that you see that the electric heating reduces due to warming and also electric cooling increases, then you see this gradual and seasonal shift in demand from winter to summer, which of course should be basically a positive signal, I think, in terms of security of supply. So I think historically winter months has been much more tight in terms of supply issues in general. The other thing is, if we think of the implications and what we have seen in the topic of hydrology, we see that there are regional differences. And so while there might be at some point, I think, stress points in some areas, there are other areas that will profit due to increased water inflow. So just beyond hydropower plants as such, I mean, climate change may have different regional effects on plant efficiency, and also in this case then on the implications of security supply. So I think, and what we also say in the next steps is, of course, that anticipating such effects in a more regional analysis is also certainly important to understand the issue of security supply in combination with climate change. I hope this gives a little bit an answer, at least from the point of view of the demand and hydrology topics that we have covered here.
Excellent, thank you very much. I hope that answered the question as well. Let's see, so another question, I think one for you, Philip. Are renewables more sensitive to climate change than traditional energy?
Yeah, thank you, Matt. The answer depends probably a little bit. I would guess renewables are more dependent on weather patterns. So they are, of course, more directly linked to climate-related things and also weather. So I would say that renewables have kind of a higher risk or higher vulnerability to climate change or to a climate problem, let's call it that way. But of course, a thermal generator has always the luxury to choose and pick the hours where he's going to produce and where he's going not to be produced. So that is a considerable advantage. But on the other hand, as a thermal generator, you're affected through the river, cooling water availability, as we touched upon, and maybe also some fuel supply chains might be interrupted or so affected. So a coal transport over rivers, for example, could be interrupted. So there is also a downside for thermal generators. But in general, I would conclude that for renewables, the exposure and the exposure is somewhat higher to the climate change.
Yeah, I mean, I guess it should be no challenge really to that, given you know, weather-related risk on renewables. The other thing, of course, is for the thermal. You know, if there are water-cooled generators, thermal water-cooled generators, CCGTs, or combined cycle gas turbines, then there's always the option of going for air cooling if one thinks the payoff is worth it. But there's not so many options for wind when it's not blowing. So with that, I think we will end the webinar there. If you flick on to the next slide, as we're pretty much up on time, you have Philipp and Claus email addresses there if you want to reach out and ask any more detailed questions that you haven't done so far, or if you've got any suggestions, we're happy to have them. And then the next webinar is going to be on Thursday, the 3rd of September, AI in the energy sector, preventing accidents. So please do sign up for that one as well. And with that, I'd like to thank Philipp and Claus. Thank you very much. And also for Johnny and Bev and my helping put these webinars on, as always. So thanks very much, everyone, and hope to speak to you next time.